What's up, everyone? My name is Dr. Chris Hacks, and today we're going to be doing the CryptoPals Crypto Challenge, challenge number 6, breaking a repeating key XOR. So if y'all remember back, we implemented a repeating key, and today we're going to be executing a method to actually break it. So this challenge isn't really difficult, it's just there's a lot of places where you can go wrong, and there's a lot of error-prone places, but we're going to do it today. And then once we do this one, we're going to be set to do all the rest of the challenges. They'll be about the same level of conceptual difficulty, but if we can do this, then we're going to be good for everything else. Okay, so let's jump right in. So over here we have a file. It's been base 64'd and encrypted with a repeating key XOR. So I already downloaded this file. It's in our project right now. And today we're going to be decrypting it. So here's the steps. They actually make it quite easy for us. They give us all the steps we need. So we're going to be trying to guess the key size first. So we're going to try values from 2 to 40. Once we find a key size, we're going to check if it's a good key or not. The way we check if it's a good key is we're going to compute something called the Hamming distance. So the Hamming distance is the number of differing bits. So I'll show you all what that means. And they give us 2 test strings and the answer. So we got to test our Hamming distance function after we write it. Okay, now once we find a key size, we're going to calculate, we're going to take the first key size worth of bytes and the second key size worth of bytes and find the Hamming distance between them, and then normalize it by dividing by the key size. This is so that when you get bigger and bigger strings, you'll have higher and higher Hamming distances, so you divide by the string size in order to get an average. And then whatever has the smallest normalized edit distance is probably the key. Or it could be perhaps the 2 to 3 smallest values. So we'll go through that and we'll check to see where we're at. Okay, once we know the key size, then we can start breaking the ciphertext into blocks of key size length, transpose the blocks, which we'll go on to do later on, and then solve each block as a single key XOR, so on and so forth. And that's how we're going to break it. So we'll go step by step, but let's start with actually writing our Hamming distance function. Alright, so I already have challenge 6 all set up here. I have our 2 strings already in here. So let's go ahead and write a Hamming distance function. So let me close all of this real quick. First, I'm going to add a new function declaration here, and it will be an integer. So int Hamming distance, we'll take 2 strings. I can make this constant actually, just because these strings will not be changed. And input 2. Once we have our 2 strings, we're going to iterate over every single character and check the Hamming distance. I also included bit set and algorithm. Those 2 headers are going to be very useful later on. So if you guys are following along, make sure to include these as well, because I'll show you why in a second. So first, let's jump over to our encoding utils file, and we're going to actually declare our function, or define it, I mean. So the first things first, we need to make sure the 2 strings have the same length. So if input 1.length is not equal to input 2.length, then we will just return -1. You can do a couple of different things if they're not the same length. However, that's kind of outside the scope of this. So we'll just assume both strings are the same length. And for our decrypting, we're actually only going to be using strings of the same length. Alright, so what we'll do next is we're going to calculate a distance. So I'm going to create a variable to actually hold the distance. We'll call this total distance, because it will be for the whole string. And then what we'll do is we'll iterate over the string. So for int I, or we'll use a size t, it's all going to be positive, size t I equals 0. I is less than input 1.length, because it'll be the same length, and then I++. Now what we can do is we can calculate a Hamming distance. The first thing we're going to do is actually XOR the bits together. So let's say, for example, we have character A. So I'll pull that up here. That's going to be char 97. So it's going to be 128, 64, 32, 1, 2, 3, 4. I need an extra 0 there. So here we have 97. And let's say we have another character. Let's say we have, I don't know, let's do something a little bit further away. We'll do E. Okay, so E is 101. So we have 0, 64, 32, that gives us 96. And we're aiming for 101, so that's 5 more, so 0, 0, 4, 0, 1. Okay, so let's find the Hamming distance between these two. Actually, let me do F, just so we can get a little bit bigger of a value. So the Hamming distance is the number of edits you need to make in order to convert from one string to another. So if we look, we can just count the differences. So there's 2 differences here and a difference here. Now, you could iterate over all of the bits in each character. However, there's a little trick we can use. We can use the XOR function. If we use the XOR function, it will highlight any differences for us by placing a 1. So all of the zeros that are the same will be XORed into a 0, and all the ones that are the same will be XORed into a 0. So what we can do is XOR the 2 characters together and then just count the number of ones. And there's some built-in functions that make that very, very efficient, very quick. So first we can just get an unsigned char. I'll just call it X for now. And we will do this. We'll static cast, and I'll cast it to unsigned char. And I'll static cast the first character, which is going to be input 1 of I. Okay? And then I'm just going to use the XOR function, and we'll do the same thing. We'll static cast unsigned char input 2. And by doing this, we just get the XOR output of the 2 characters. And we can count it very easily. There's a built-in function. It's a std bit map? No, it's a bit set. That's what it is. A bit set of 8 bits, and we do X in here, and we do count. This function here will give us a size t for the number of bits that were actually 1 in this bit set here. So now all I can do is I can do total distance plus equals static cast int, and we can just put this in here. And what this will do is it will count the number of ones and add it to our total distance. By iterating over every character in the 2 strings, we can get the total distance, or the total Hamming distance, and that should be our function. Alright, cool. So let's go ahead and actually test this out. So what I'll do is I will call, what do I call it? I call this Hamming distance. And we'll pass in test1 and test2. I'm actually going to return this. Let's just return this. And I'll call std2string, just so everything gets converted over correctly. Alright, so now when I go ahead and run this code, we should get an answer of 37. I'm not going to do it by hand, since they already provide us with the answer, but if you were to do it by hand, you get 37. That's what our code gives us. Perfect. So now we know our Hamming function, or our Hamming distance function, is actually correct. So I'm going to go ahead and delete all of our test cases, and we'll move on to the next step. So the next step is to actually figure out the key size. So what I'm going to do is I'm going to create a new function. We're only going to use this function in this challenge, so I'll put it in this file, the challenge6 file. We'll call it find key size, and we will pass in data. So it'll be a const the string reference data. Cool. So now the first step is to guess the key size. Okay, so they give us a range. They're going to say try values from 2 to say 40. So depending on what you're decoding, the key size could be much bigger than that. Can't really be smaller than that. It could be 1 potentially, but that's not necessarily going to be the case. So it just depends. But what we'll do is we will use their range. So for size t I equals 2, I is less than 40, and then I plus plus. So we'll use their range, and that's going to be our key size. Actually, I'm going to call this key size here, just so that we can keep track of this variable a little bit better, because that's what we're actually measuring here. So the next thing we need to do is compute. We need to find the Hamming distance between the first key size of data. So that's pretty simple to do. We just need to grab a key size worth of data. And in order to do that, here is what I'll do. I'm going to, let's see here, key size, okay. So what I want to do is actually just get the first 4 blocks. Because what we're going to do, say we have a key size of 4, we're going to compute the Hamming distance between, or this is 4 bits. We're going to be talking in terms of bytes. Each key size is going to be 1 byte. But just for simplicity, I'll use bits here. What we'll do is we'll grab the first 2 blocks and compare them. Get the Hamming distance, divide by the key size, and then hold on to that. We'll do it for the same thing for the next 2 blocks. We'll add it to an accumulator once we get the Hamming distance, and we'll do it for the final 2 blocks. Once we get the 3 Hamming distance measurements, we can go ahead and divide by 3 and get the average. And that should give us a little bit better of a measurement than just looking at the first 2 blocks. It'll give us a little bit sample size. A little bit slower, but it gives us more reliable, more accurate results, especially in the real world. So what I'll do is I will grab, actually what I'm going to do is make another for loop. For int I equals 0, I is less than 4, and I plus plus. We'll grab our blocks like I was just demonstrating earlier. So let's grab our first block, we'll call it block 1, and we're going to pass in data.begin, and we're going to add our key size times I. So that will give us the first, but that will put the starting position at the first part of the block, and then later when we move on to later blocks, it'll move us along 1 key size distance. And then the second measurement will be, I call this data, right? Alright, whatever. Call it data.begin, and then it's just going to be key size times I plus 1. Alright. That'll give us our first block, and then for our second block, it's almost the same code. It's just going to be block 2, and then we just have I plus 1 here, and I plus 2 here. So that will give us our 2 blocks. And then what we can do is calculate the Hamming distance. We'll do double distance equals Hamming distance between block 1 and block 2. We'll divide cast double, and then we'll have our key size. This will make us use this will convert key size to double. That way we can do double division. So it's actually a floating point operation rather than an integer operation, and we can actually keep our precision. We store that double in distance, and then actually we probably won't even need a variable. Let me declare this first. Double total distance. I don't even need to include distance. I can just increment total distance. Save us a variable. All right. So we'll keep track of our total distance, and then this will run 1, 2, 3, 4 times. So this will actually get us our first 5 blocks. We only want the first 4, so let me chop this down. So it'll run for, yeah, this will compare the first 4 blocks and do 3 comparisons, which is what we want. So now what we'll do is we'll calculate the average distance. So double average distance equals the total distance divided by 3. And I'll put 3.0. Total distance is double, but we'll just make both of them a double. Okay, and then if we actually go back to the instructions, let me pull those up real quick. It does say that we can find the first 2 to 3 key size values. We might actually want to do this because potentially smaller key size might score a little bit better. So what we'll do is I'm actually going to do that. I'm going to, instead of just having like the best key size, I'm going to have a vector. I'm going to return a vector. And it will have our it'll include our key sizes. So vector int. Yeah, that's what we want. All right, perfect. So the reason why we're going to return a vector int is just because we want to find the 3 best key sizes, for example, like the instructions suggest. We are going to need some sort of container to actually hold our key sizes. So what I'm going to do here is I'm going to make a vector, and I'll put a standard pair in it. And what the pair will do is it's going to have a double for the actual Hamming distance average, distance score, and it will have an integer to hold the key size. So that will allow us to sort that vector and get our 3 top key sizes. So back down here, what we can do is distances dot push back standard. We'll make a pair because that's the function to create this, and we can put av distance and key size. So that will keep track of our key size that we're looking at and the average distance. Okay, perfect. Yeah, so that should be good. That should be good. Okay, so now I can also reserve up here, I'm pretty sure. Let's see here. Yeah, we can reserve here. So let's do that as well. Distances dot reserve, and I'll reserve, let's see. We'll be lazy. We'll just reserve 40. Just even though it's probably gonna be only like 39, but or I guess we can put 39 because it'll be 2 all the way up to 30. I guess it'd be 38, huh? You're gonna do key sizes 2 to 39 inclusive. Yeah, so it'd be 38. Okay. So we'll reserve 38 spots just so we have enough. Okay. Yeah, so that should all work. Oh, one more thing. Let's actually add an error check. If key size, let's see. So we need to actually make sure that there's enough data for our key size to compare against. If we don't do that, then what will happen is we could run out of data, and that could cause some issues because then we'll be looking at blocks that are further than the actual endpoint. So what I'll do is I will do if key size times 4, because we'll be looking at 4 blocks. If that is greater than data dot size length, I'll use length just to keep it consistent here. It's weird how there's the 2 different functions. They do the same thing, but yeah. Okay, if there's not enough data, then we can actually just break, because if we get a bigger key size, there's still not going to be enough data. So we can just break here. There's no reason to continue on. All right, so once we do that, we can go ahead and start actually looking at we already populated our vector. So yeah, so we don't even need to do anything. We can just sort it. So let's do this. Here are going to be our best key sizes. Best key sizes. Okay, so now we'll actually collect our best key size and get ready to return them. We'll go ahead and sort yes, we'll sort our distances vector. Should use something efficient like merge sort, so it shouldn't be that big of a deal to just call this function. Plus it's pretty small, so it should be efficient. Alright, so we'll sort that and then we'll just get the first three. So yeah, all we need to do is just do this. Vector, or I'm sorry, this is going to be best key sizes. Push back, and we can just push. We'll do 3. I don't need a for loop because this is going to be constant. We're going to use distances dot. Let's see here. Distances of 0 dot second. Yeah, that's what we need. And we can actually just copy this. So I can just increment these. So that will give us our 3 best key sizes. So we can just return best key sizes. And because we're only pushing back 3 elements, we shouldn't need to reserve any space. It should already be reserved. It should be large enough. Okay, perfect. So yeah, that's all there is to it. That's the function to find the key size, according to the instructions at least. So if we go back over to our instructions, yeah, now that we found the key size, we can actually start doing stuff. All right, so now that you know the key size, let's break the ciphertext into blocks of key size and length. We'll transpose the blocks, so that means make a block that is the first byte and a block of the second byte, and so on. So we're just splitting the data up into blocks of key size. Solve each as it was a single character XOR. We already have code to do this. For each block, the single byte XOR that produces the best looking histogram is the repeating XOR key byte for that block. Put them together and you have the key. Alright, so we'll be using our heuristics function a little bit. So now that our find key size function is complete, let me actually call it real quick. So I guess we can do that at the end. I won't bother with that. I don't think we need to test it or anything. We can do that in the debugging phase. All right, let's find our next function. So the next function we're going to create is going to be called key or find key, because it's just finding the actual key. So we're going to return a string for the key. Find key. And what we'll do here is we'll pass in the key size, and we'll pass in the data. All right. So first things first, let's do this. Let's transpose our blocks first, just like the instructions say. So for size t I equals 0, I is less than data dot length, and then I plus plus. We will let me create a vector for this real quick as well. We'll call it blocks. And so we'll have a vector of string called blocks, and we will reserve key size. Yeah, wait. No, hold on. That doesn't make sense. Hold on. Yeah, no. That's not how we're gonna reserve space, because that's not the right amount. So we're not even gonna worry about reserving space here. Oh, hold on. I actually need that vector. Okay, so we'll have our vector. We'll let it reserve space on its own. But yeah, so what we'll do for blocks of I modulus key, such an inefficient operator, but it is what it is. For I modulus key size, we can do dot pushback data of I. Yeah. Yeah, that should do it, I'm pretty sure. So yeah, so that's what we want, because the first byte of every single block will become part of the first block, and so on and so forth. So let's say, for example, you have like um, this block, and I'll use bits instead of bytes again. Basically, what it's going to do is it would break it up into 4 blocks, where it'd be like 1, 1, or I'm sorry, 1, 0. It's going to grab this bit and this bit for the first block, and so on and so forth. But we're just working with bytes here, so 8 bits. But yeah, so this is what we want. Alright, so I'm just thinking, okay. So yeah, so that's what we want. So next, after we actually transpose our blocks according to the instruction, we're going to solve each block as if it was a single key XOR. So yeah, not too bad. We already have the code to do this, but yeah, we already have the code to do this, so we don't need to do anything too crazy here. Alright, so I'll probably just rewrite the code. There's not a big deal, just because I don't want to be calling a function multiple times here. So, okay. Let's do this. So we're going to solve each block as a single byte XOR. So first, for size t, I equals 0. I is less than key size I plus plus. So we need to score this. Okay, we're going to be decrypting the block, and then we have to score it. So I'm going to hold on to a variable called score. Best score equals, we'll just call it, -1. Because all of our scores are normalized to be higher than that, between 0 and 1. So that'll be the lowest score anyways. Next, what we can do is we have to actually figure out what the key is. So unsigned char best key char, and we'll just set that to be the 0 character for now. Alright, so now we have to actually iterate over every single character. So I will call it I'll put unsigned char, and we'll call it C equals the null character. Or I guess I could put 0, it doesn't matter. Same thing. And then we'll just do C is less than 256 and C++. That'll give us our character, because we're trying to build the string, the key. The key is going to be just a bunch of different characters. So we'll build that up real quick. Alright, so unsigned. Wait, hold on. What am I going to do here? So let's do this. std string decrypt, and we'll put in blocks of i.size, and we can reserve enough space using this sort of setup. And then what we'll do is for size t of k, we'll actually decrypt it like this. Yeah, like this. Okay, so what we're going to be doing is we're going to go iterate over every single byte, every single character in our first block. And what we'll do is we will XOR it like this, like so. So decrypt is just equal to, decrypt of k is equal to blocks I, k, XORed with the C. Alright, so let me explain real quick what this is doing. So we have our outer for loop going over every single block, and then we have our inner for loop going over every single character that we want to try. So what this inner for loop is doing is that for every single character in the first block, we are going to decrypt it. So decrypt of k, which is the character we're on, we're going to take the first block and the first character from that block, XOR it with whatever our test key is, and then store it in decrypt. This will build us a decryption string. And once we have this decryption string, we can score it. So I'll score it real quick. So double score equals just score human. What did I call this? It is called, oh, we need to get heuristics real quick over here. This is called score text. And I need to include that. So include heuristics.h, and we're going to do double score equals score text, and we will pass in decrypt. I need to actually declare that inside of this loop so we can actually score it. All right, and then if our score is better than our best score, then what we can do is we can just set best score equal to score, and then best key char is equal to C. And there we go. Now that will score whatever we decrypted and store it. Yeah. So once we store it, we're going to start building our actual string. So I need to actually hold that. So we'll create a string up here, std string key. And I believe I can just pass in key size. Yeah, I can pass in key size. And we'll just fill it with null bytes for now. And what I'll do is that for each item in the key, we'll just do best key char. And that will build our key. Perfect. Okay. And then we can return our key, because after all of that's said and done, we'll get our key. Yeah, and that's all there is to it. Okay, perfect. So I'm pretty sure that's it. Yeah, and that should be our find key function. Okay, I don't think I'm missing anything. All right, so now we can actually put it all together. So first things first, we are going to read our file into a buffer, or into a string. So what I'll do is I'll do it this way. I'm going to do it this way. We'll use a string stream, and we'll call it buffer. Buffer. Just make sure. Oh, do I need to import it? I need to import it. All right, hold on. Let's see. Import library. I believe it is. Okay, it's called stream. So let me put that in the challenges just so that we have it for everything. String stream stream and include stream. Okay, that will give us access to our stream. Okay, because we're only going to be writing into our buffer. All right, so from here, what we can do is we can actually write file. No, it's read. Oh, what was it again? It's like Hold on, let me all right. Okay. So it's gonna just be, yeah, it's just gonna be this file dot read buff, like that. Okay, perfect. Perfect. So now once we have that, we can go ahead and decrypt it. So yeah, we'll call it string data equals this is base 64 encoded, so base 64 to text buffer dot string. All right, so that will put all of our text. It will convert it from base 64 into text and then load it into data. From data, we can go get our best string key sizes. So yeah, what we can do is we can actually call find. Yeah, and then we'll just measure everything. Okay, yeah, perfect. So find key size of data. Okay, and then with that, we will do std vector int key sizes equals find key size of data, and then we need to actually find the best decrypted message. So what I'll do here is, this is a little inefficient because we're going to be checking 3 keys rather than 1, but it does make it guaranteed that we will find the message, or at least better chances. Alright, and then I can actually put in here I'll just reserve. I'll use the reserve function because we know what the size is. Best decrypted message dot reserve, and we'll put data dot length. And the reason why we're doing this is just because we're going to be copying stuff around, and we already know what the size is going to be, so might as well reserve it if we already know the size. Alright, so for int size in key sizes, we can just use a for each loop here. Whatever the key is just going to be find key of size. Wait, hold on. Key sizes. And let me make this lowercase. Alright, so find key size of the size and the data. And then we'll just do string. So even though we can find the key, we still have to actually decrypt our string. Let me use our built-in function. Yeah, we might as well. So what did I call it again? It is called repeating XOR. Repeating XOR, and we will put inside put in our data and our key. Yeah, just like that. So that'll give us our decrypted message, and then double score equals score text, and we'll put in our decrypted. Yeah, and then if score is greater than best message score, I'll just call it best score. No need to get. Let's call it best score. If our score is better than our best score, what we can do is best score equals score, best decrypted message equals decrypted, and then best key. Yeah, we'll store our best key as well. And it could be anything, so I'm just not going to put anything because it could be 3 different lengths. So we'll just best key equals key. I guess since we're copying, we don't even need to do this either, huh? So yeah, that should be good. Okay. So yeah, so once we have that and we went over all that, then we should just be able to return. So return best decrypted message, and then I'll just AND it with let's see here, what do we want to put? Put a new line, and then we will put key, and yeah, let me use the AND operator. Put this. I'm working in VB at work and C#, so I'm so used to using the AND operator instead of the plus. Okay, so message message key best key, and then we don't need the score. We can just hold on to that. All right, that should be it. If everything goes well, let's just run it and see what happens. It should be a little bit slow because we are doing multiple for loops, but hopefully it goes quick. Assertion failed. All right. Vector subscript out of range. Let's see, abort. Let's go figure out what went wrong. Alright, so first things first, let's change this to 255 just so that it doesn't get mad at us there. And then ill-defined loop body. It keeps giving me this error. It's been giving me this error in like all of our earlier challenges. The loop should be executed just because. Yeah, so it was saying the error is coming from here. Something's going wrong here. So let's see, blocks, dot key size, push back. Oh. Let me try this. Key size, like that. See if that fixes it. That may fix the issue. Yep. There we go. Okay. So yeah, so we did have to reserve the correct amount of size, otherwise it got mad at us. I still don't know why it's throwing this error. This is just straight up wrong. Obviously our loop's being executed, but anyways. So yeah, let's just run it. So we go through, we get our message, I'm back and I'm ringing the bell, blah blah blah, all this stuff, and then comes down here, key terminator X, bring the noise. So let me actually clean that up a little bit and then we'll commit everything. So we don't need the message here, we already have challenge 6, and then I don't need that space there. I can run it again, but yeah, so what it's doing is it's going through, it's checking everything, and we just broke the cipher. So I'll actually open up the file and show you what's in there. It's just a bunch of base64 encoded data. It comes out as weird garbage when you actually read it out, but you do all these steps in the challenge and it breaks the data. We can break the encryption. So let's actually go back and see what it says. So yeah, this code is going to turn out to be surprisingly useful later on. Breaking repeat key XOR, or the veneer cipher. It's an academic exercise that a lot of people know how to do, but no one actually does. So that makes us special because we've done something impressive. We broke a cipher that, I mean, is well known, easy to break. However, most people haven't done this. So definitely good exercise. So thank you all for watching, and I'll look forward to seeing y'all in the next video.